I'm going to take active low pass filter in this video lecture. Active low pass filter using op-amp, its classification and frequency response will be discussed in this lecture. The filters are classified as active filters and passive filters. What do you mean by active filters? Active filters uses op-amps along with combination with resistors and capacitors. It provides amplification along with filtering. It has better performance compared to passive filters. The frequency response depends on R and C values which is used in the construction of the circuit. An active low-pass filter uses an operational amplifier combined with resistors and capacitors to allow the low-frequency signals to pass while attenuating or rejecting the high-frequency signals. Unlike passive filters, active filters provide voltage gain and prevent loading effects due to op-amp high input impedance. The non-inverting configuration of the active low-pass filter is given in the circuit diagram. In this, the input signal is given to the non-inverting terminal through the RC section and R1 and RF is connected to the inverting terminal. Hence, the op-amp act in the non-inverting mode. So, by using the potential divider rule, the voltage at the point inverting terminal is calculated using the formula and the signal is filtered by the RC network before entering the non-inverting terminal. This provides a positive gain and high input stability. The cutoff frequency is calculated as Fc is equal to 1 by 2 pi RC. The Fc is also known as break frequency. The gain of the circuit is given as A max is equal to 1 plus Rf by Rin, which is also called as passband gain of the amplifier. Rf is the feedback resistance and Rin is the input resistance. Hence, in the first order active low pass filter, one RC section will be used, whereas in second order low pass filter, two RC sections are used, and hence here the roll off rate will be minus 40 dB per decade compared to 20 dB per decade in the first order low pass filter. So it meant that it blocks the unwanted noise much faster than the first order low pass filter. Now we analyze the frequency response of the low pass filter. It is given in the graph description in the slide. The frequency response of the low pass filter, it describes how the circuit's voltage gain and phase shift changes as the input frequency increases. It is typically visualized using a Bode plot in semilog graph shape. The gain remains constant at low frequencies as mentioned in the figure, which is called as passband, and it begins to drop off after the following feature, which is the cutoff frequency. For the first order low pass filter, it is given as the transfer function of j omega is given by Emax divided by 1 plus j in f by fh. The magnitude of the gain in dB is given as 20 A max divided by root of 1 plus A by F. So, for the F is less than FH, the gain is approximately equal to AF. So, that's what the, it is the low band. This is the For second or low pass filter, it will be minus 40 dB per decade. That's which increases with frequency. It is used in audio and noise reduction application. An active high pass filter allows high frequencies to pass and attenuate low frequency. The cutoff frequency FL is given as 1 by 2 pi RC. The gain increases up to the pass band at the rate of plus 20 dB per decade. The construction of the circuit is given as the input signal passes through the capacitor and with a resistor are connected to the ground. The junction then feeds into the op-amp. At low frequencies, the capacitance has high reactance and blocks the signal. At high frequencies, the reactance drops and the signal passes the op-amp for amplification. The frequencies below FH are attenuated. The gain increases at a constant rate plus 20 dB per decade up to the cutoff frequency FL. After the cutoff frequency FL, it passes through the constant gain, which is referred as pass band, as shown in the frequency response characteristics in the slide. The phase shift is the output signal leads the input signal. At the cutoff frequency, the phase shift will be plus 45. It is used in communication circuit, audio tweeters, AC coupling, vehicle equipment. An active band pass filter uses the specific band of frequencies to pass through while attenuating or rejecting both lower and higher frequencies. The basic configuration is given as cascading of low pass filter and a high pass filter. It is a combination of low pass and high pass filter. So initially it is followed by a high pass filter followed by an low pass filter. It blocks the low frequency signals. Its cutoff frequency defines the lower boundary of the pass band, and a low pass filter will block the high frequency signal. Its cutoff frequency FH defines the upper boundary. For the filter to work, the low pass cutoff frequency must be higher than the high pass cutoff frequency. The Bode plot shows the mountain shape of the frequency response of the bandpass filter. The peak gain is at center frequency. The attenuation of frequencies is below FL and above FH. The center frequency F0 is given as square root of FL into FH. The roll-off rate occurs at a plus or minus 20 dB per decade for the first order low pass and high pass filter on either side of the pass band. Then with respect to phase shift, the output leads the input at low frequencies plus 90 degree and is in phase 0 degree at center frequency and lags at high frequencies at minus 90 degree. The major applications of the bandpass filter are audio equalizers used in wireless communication and in medical equipments, isolating the specific heart or brainwave rhythms from the noise. In case of audio equalizer, it splits the sound into bass, mid and triple bands. To mention a few applications of op-amp filters are in audio processing systems, in audio equalizer, communication systems, signal conditioning, and in biomedical instrumentation, mainly in ECG and EEG equipment. Thank you.